All right, hello everyone. My name is Charles Fan. I'm co-founder and CEO of MemVerge. It is great to be here again at the Persistent Memory Summit. I guess we also have computational storage now as part of the theme. I think last year when I mentioned I had a pretty raw slides and we didn't have a marketing person, and I'm happy to report that we do have a marketing person now. Frank Barry, and you will find the slides this year is a bit more polished than last year's. So happy to share what we do in big memory software. And in particular, another progress we made is we actually work with the customer and identify specific use cases over the last 12 months, how they are using persistent memory as well as memory machine software that we produce to help their particular applications. In particular, I'm going to share 4 of those use cases, and I'm sure we'll have more in the coming years. Okay, so first, if we look at this overall infrastructure space that we are working on, we believe that there are 3 major trends that are happening. It's going to become multi-cloud. On-prem is not going to disappear, but workload are moving to cloud, and this is accelerated over the last year by the COVID pandemic, and that we are noticing a clear trend that's accelerating, which is the enterprises moving the workload to the cloud. We also are seeing the starting trend of becoming more memory-centric for the infrastructure, and the applications become more memory-centric. This is driven by the growth of data in capacity and in velocity that only the memory media has the performance to handle it. And increasingly, these infrastructure resources will be consumed as software and becoming more composable at the same time. So we think the 3 clear trend is multi-cloud, memory-centric, and software composable. And that's the world we are going into. And at MemVerge, we hope the software we produce will be a catalyst in movement in these 3 directions. In particular, the concept we are promoting is called big memory computing, and this is because the data are becoming both bigger and faster. So on the left-hand side, you see more and more applications are dealing with bigger and bigger volumes of data. On the right-hand side, you'll see that there are more and more real-time applications that need to process data with lower latency. And the intersection of the 2 circles are becoming bigger as well. And this is the area where the memory-centric infrastructure will be key. And how big memory software works is that we can virtualize various kind of memory components, memory media, through different memory fabric that we can virtualize them, make them abstract, and supply them as software-defined memory to the applications. So it hides the complexity of the underlying memory, which are going to become more heterogeneous, with 3D cross-point as well as other persistent memory emerging, and so that the applications, both existing applications as well as new applications, can live happily on top of this new infrastructure. And there are many of these applications. So here, just giving some examples through different verticals and different layers of the applications that we believe going to move to a more memory-centric infrastructure. From the cloud service provider, cloud infrastructure, virtualization layer, to the containerization layer, and Kubernetes, etc., and to the various databases, in-memory databases, as well as classical RDBMS, and then the AI, machine learning, big data analytics. All those applications cannot have enough memory. The more memory, the happier. They can achieve higher consolidation ratio, they can achieve higher performance, they can achieve lower cost for their infrastructure. And this can help across various industries, from financial to healthcare, biosciences, to media entertainment, social media, retail, you name it, every industry is becoming a data-driven industry. And the memory machine software that we shipped last year in 2020 delivers big memory without compromise. That we can deliver a new price performance point for memory. We can reduce cost by 30 to 40% per gigabytes, and there are additional cost savings from the higher consolidation ratio we can achieve. And through software innovation, that we can deliver DRAM level performance without penalties while you're enjoying bigger and cheaper memory, and can deliver higher performance for the memory hungry applications where the capacity of memory is the bottleneck. There's a problem called data greater than memory, that increasingly those applications can put as much data in memory, and the overflow goes to the SSDs. Once the data start going to SSDs, you incur storage I/O, the performance drops. Where if with bigger memory, you can fit more or all of the data in memory, then the performance is much faster. So this is a performance enhancement through big memory solutions. We also invented a new innovative data service on top of memory called in-memory snapshot. And what memory snapshot are able to do is capture the running state of the entire application process, so that this point in time can be recovered, restored anytime in the future. And through this way, you have some very interesting capabilities that can be enabled, allow instant application rollback, branching, cloning, and crash recovery. This can introduce new user experiences, delivers higher productivity and availability to the interactive memory-intensive applications. And we can do all of this without changing your application. So this software would just plug in and allow your applications to run faster, run cheaper, and with higher productivity, newer user experiences, and higher availability as well. And that's the benefit the memory machine can deliver. Okay, so now let's dive into the 4 use cases that I alluded to at the beginning. These 4 use cases are, number 1, we have been working with some cloud service providers to lower the cost of their cloud infrastructure by delivering bigger memory solutions. Number 2, we have been working with some customers for their database infrastructure to deliver better availability and high performance to those environments. Third, we have been working with some bioscientists in the genome sequencing and analytics. In particular, I'm going to give an example how we are working with one of our customers in the single cell RNA sequencing. How do we make that process much faster, much more efficient and productive? Last but not least, we have been working with companies in media entertainment, in the animation and special effect, how we can make those movie making software also becoming higher available and deliver the user experience that's not possible before, that you can roll back much more easily of your applications. So I'm gonna go into these 4 use cases, give you some more details, and also end the presentation with some look towards the future. So first example, for the cloud infrastructure, for those who know, the most quintessential service they provide is a compute service, and those are usually driven by virtual machines. And users would rent a virtual machine for a period of time or forever, and paying the rent to the cloud service providers. And so a key consideration for the cloud service provider is a cost basis for each of the VMs they are providing it. And that determines how low a price they can charge, how competitive they can be, and what's the margin they can make on those VM services. And so VM density is really the money. If you can have higher density, have more VMs per server, you lower the per VM cost, you increase margin, and you can make your service more competitive. So this is a core to the business model of cloud service providing. And what we are working with those cloud service provider is using our memory machine to manage between the DRAM and persistent memory, so that the amount of memory available per server is increased. And in our memory machine layer, we can deliver this in a DRAM compatible way to the hypervisors, where hypervisor suddenly has more memory at its disposal. And if the memory was the bottleneck on the provision of new VMs, now you can create more VMs per server, thereby lower the cost per virtual machine. And we are doing so without changing the hypervisor or changing the applications, as we are glibc compatible, that we can intercept the necessary memory costs from those hypervisor and allow those VMs to run. And we can deliver very high performance as well. So one of the reasons that these service providers are using us instead of just the memory mode coming with Optane is that we can deliver a better performance isolation, less of a noisy neighbor problem between each of these virtual machines. Is because with memory mode, it's done on the hardware. It's a nice solution, but it has the same DRAM pool for all the server. So if there's one VM that's running away, it could slow down the other VMs. Where we are allocating for each of the VM its own set of DRAM and PMAM, so that it has better isolation in terms of memory resource consumption and reducing the noisy neighbor effect between these VMs. So that's a good reason that it's an ideal fit for these cloud service environments. Okay, and so here is sort of some basic numbers. On the left-hand side, you can see the noisy neighbor effect that I just described, where you get more even performance across all these processes. On the right-hand side, you can have an estimate using Optane plus DRAM. You can achieve a significant cost saving on both the memory cost as well as the overall server cost. So in this case, essentially for the same amount of memory, that if you're just using DRAM only, you are spending $2 million. If you make the right mixture between DRAM and PMAM, we can deliver near DRAM performance at a cost of $1.48 million. You save at least over a quarter of the overall cost by moving to this persistent memory scheme. So that's the first use case. The primary driver is TCO reduction. It can reduce the cost basis for a cloud service provider. Just reducing 25% is a big deal because that literally opened up the margin for those cloud service providers. And the second use case are with the databases. As I mentioned before, with the databases, especially the newer kind of in-memory databases, graph databases, and so on, when you can fit the entire data set in memory, it's fast. Once you start keeping some of them in storage, it becomes slower. And it's not just a little bit slower, it could be 10 times, 100 times slower. So the performance drop is falling off a cliff. It's pretty dramatic. So that's sort of a gap that the customer would like to bridge. And the secondly, the memory has been expensive, and they have a limit to how large it can go to. And the memory size does limit how much data you can keep in the database and how many instances or shards you can create on each of the server. And with a bigger memory solution, hopefully that can be improved as well. And then as memory getting bigger and bigger, the risk of losing the data in memory become bigger as well. And that becomes a more significant consideration for the customers. So they're looking for a way that they can protect and recover from failures in a better way. So these are some of the pain points with the database infrastructure that we have been solving together with customers. On the capacity front, DRAM is smaller. Now if you have persistent memory, it becomes bigger, and you can certainly choose to use the memory mode from Intel to do it. And that's a caching algorithm, 2LM caching algorithm, that gives you a bigger memory capacity. And in this example, if you have 384 DRAM, gigabytes of DRAM plus 1.5 terabytes PMAM, with Intel memory mode, you get 1.5 terabytes of DRAM compatible memory. And with memory machine, we can also do so, but because of tiering algorithm, we can get the combination of the capacity, 1.9 terabytes available to the applications. And then as you can see, snapshot is possible on this, which take advantage of persistence nature of the memory, so that it's not only volatile, but the persistence capability is available if you need it as well. So number one is it has a somewhat higher capacity than the alternative ways of using persistent memory, and therefore you can fit more shards or more members in the Hazelcast case. In the left hand is Redis case, right hand is Hazelcast case. Those are two very popular in-memory KV stores or in-memory databases that we have been supporting with the customers, and more shards, more performance, and less cost. And then on the performance, people are often asking us, from customers and partners, how much overhead do you add given your software tier? And what we are demonstrating here is actually very interesting. Is that with with our software running on top of memory, it actually does not add overhead comparing if you're just using OS, operating system, and DRAM. Here, the purple bar is with our performance. The gray bar is with just the operating system and DRAM. You see it's almost identical performance. Sometimes we are a little faster, sometimes we're a little slower, but it's all within noise, 1 or 2% of the performance. And then we can, through our snapshot mechanism, make the database snapshot recovery much faster versus the previous method. If you use RDB method within Redis or you use hard restart within Hazelcast, it's a longer process to save it onto disk, where we are just taking a snapshot and save them on the persistent memory. And we can do so repeatedly by only capture the deltas, the pages that have changed. So both the snapshotting itself and the recovery process, which showing here, is much faster. And these are actually real numbers from the customer POCs that we have done. So that's a very interesting use case, database that has pretty broad usage among the customers. The third use case that I'm going to share is in the genomics computing. And genomics is sort of a special case of a data pipelining sort of analytics work. It often needs to go through various stage of data processing, and is dealing with pretty sizable data, especially as time goes on. The people in this field are dealing more and more genomic informations at the same time. So you're typically looking at hundreds of gigabytes for one task that you need to do. And as they go through these stages, they often need to checkpointing the state so that they can go back to reproduce the results, or changing some parameters to do a what-if analysis so that you can compare the results to see which way is better. And doing that is time consuming. After each stage, they need to save the data onto storage and retrieve it from storage when they need to run it again, or when they need to make some changes. So that's a time consuming and process. And if you don't do so, then you cannot do it, and you also have the risk of losing data. So that's a current sort of situation and pain points with genomics computing land. And now if we're running our memory machine plus Optane or other persistent memory underneath, then you can take advantage of the memory snapshot, replacing all the storage IOs with memory snapshot and save them onto the persistent memory. And then this allow you to roll back, allow you to branch, do the what-if analysis without incur the overhead. So here are some numbers. The blue bar is the baseline. Without us, you can take anywhere between 233 to 800 some seconds for after each of the stage. So in this case, there are 11 stages. After each of the stage, it takes so much to save the data. And if you replace it with in-memory snapshot, you can do that within a second for any of the stages. And then if you include compute, some stages compute takes longer, some stages compute takes shorter. So compute still need to take place, but because of saving on the storage I/O part of the equation, you get a pretty good overall saving on the time consumed as well across the 11 stages. And this is just running through, from 1 through 11. Now, if you need to go back, you need to do the what if analysis, you need to reproduce, you need to do all that. It delivers even a greater efficiency and better user experience, basically turning batch processing into a very interactive process for the people who are doing it. So overall, you can save, really 60% of the time if you just go from 1 to Z, A to Z, or 1 to 11, go through the stages, and it greatly reduces what they call the I/O waste, the time they spend in those storage I/Os, and we can do it all in this big memory workstation there. All right, so that's the third, the genomics. Now the last one is the animation in the media entertainment. So a typical application is like Autodesk Maya. They'll be sitting in front of it and running the application. If they run out of memory, they get out of memory problems, and then when there's a crash, it's very disruptive to the flow of the artists. Usually as artists are working on this, if you give them an interruption of 30 seconds, then they're out of the zone, creative zone. It takes like an hour or two for them to get back into it. So this continuity is very important. So what we are doing is essentially creating a quick recovery process underneath these applications. So if there's an interruption, there's a crash or interruption for any other reasons, and this is, by the way, a quote from one of our beta customers, Chapeau Studios, that before it takes minutes in this case, and in some cases it takes many minutes or even hours to recover from it, and we can reduce that to seconds when they get back into it. So this way, their continuity does not get interrupted, and they can stay in the zone and complete their work. All right, so those are the 4 use cases that we are working with customer on. And let me take a couple minutes just to look at the future and conclude my talk. So tomorrow, we know that memory will become more important. There are some very exciting technologies. I think at this conference, people are talking about not only about the media, there's 3D crosspoint, there are other exciting media coming, but also about the fabric. I think CXL is really catching fire and is looking to become real over the next couple of years, and that's going to really be a game changer here. And so we think really compute will become more heterogeneous, memory will become more heterogeneous. There will be newer fabrics interconnecting them, and there will be new software that help the application use it in an easier way. And this is being recognized by the industry, including people like Gartner. And the innovations are happening on all these dimensions. There are new processors, new memories coming out. There are other emerging memories, and there are different fabrics. And we think the future, the new pyramid will be looking like this. There will be 3 tiers of memory, and this is already starting to take shape. The first tier are the memory that are close to compute, and they are either on the same chip or in the same package, or just sitting really close, like high bandwidth memory that can have very high performance, single-digit latency, very broad bandwidth between memory and compute. So to remove the von Neumann bottleneck there, and then the second tier is the DRAM tier that's connected through DDR, and this I believe will continue to exist for the foreseeable future. And I believe also there will be a third tier, the capacity tier of memory. that's emerging, already with the Optane memory. That's sort of the first of these capacity tier memory. And there will be more, especially when CXL become real. So I think this tier will be primarily CXL connected at the latency of hundreds of nanoseconds, where DRAM is at tens of nanoseconds. And between these three tiers, going to really support the infrastructure of future applications. And where our software try to help is at least help the adoption between the second and third tier. How do we virtualize them, deliver them to the applications so that they can become alive on these memory and have less dependency on the storage infrastructure. So it's a very exciting future, and we are at the very beginning of this journey and very excited about this journey that we are on. If you need more information, email us at info@memverge.com. If you'd like to have a demo, if you're interested to try it out, if you're interested in collaboration, partnership, we'll be happy to talk to you. Thank you very much.